Hey everyone, and welcome to this explainer. Today, we are taking a seriously mind-bending journey across the extreme scales of our universe. We're going to start with the terrifying, highly personal experience of falling into a black hole at the microscopic, human level. And then, we're zooming all the way out to meet the absolute largest known cosmic giants in existence. It's a trip from the deeply bizarre right up to the unfathomably massive, so let's get into it.
Okay, let's jump right into the deep end. Have you ever wondered what you'd actually see if you fell into the largest black hole in the universe? To kick things off, we really need to understand how extreme gravity completely shatters our standard perception of reality. We usually think of space as this static, empty stage. But around a black hole, it behaves way more like a cosmic funhouse mirror that violently distorts both light and time.
To figure out what happens when you fall in, we first have to talk about the event horizon. This is the ultimate threshold, the literal point of no return. It's the boundary where the gravitational pull becomes so overwhelmingly strong that the escape velocity actually exceeds the speed of light. All the original mass that formed the black hole is compressed to such an extreme density that it's entirely trapped and hidden within this boundary.
And just outside that boundary, the physics get totally wild. Because of that intense gravity, the paths of light bend sharply. Sometimes light even loops entirely around the black hole. Light from distant background stars gets stretched and warped into this stunning visual phenomenon called an Einstein ring. Plus, any material orbiting near the speed of light gets artificially brightened on the side moving toward us, thanks to relativistic Doppler beaming. Visually, it is just utter chaos.
Now here is where reality literally splits in two. There is a stark contrast between two completely different perspectives of the exact same event. Let's say I am safely outside the black hole watching you fall in. I don't actually see you cross the threshold. Because light struggles so hard to climb out of that gravity well, your image time dilates and redshifts. To me, you appear to just freeze, turn red, and slowly fade away. But for you, the doomed astronaut, you pass right through the event horizon as if it were just empty space. You wouldn't feel a physical surface at all.
As you keep falling toward the singularity at the center, your perspective radically diverges from the outside universe. If you looked back and tried to fire a rocket to escape, the universe behind you would focus into a small, highly blue-shifted window. You'd basically witness a finite chunk of cosmic time play out rapidly above you. But your journey does end inevitably. Before you even reach the center, the difference in gravity between your feet and your head becomes so extreme that you are torn apart. It's a gruesome process that physicists, and I'm not making this up, actually call spaghettification.
All right, moving on to Section 1, Phoenix A, the giant. Let's leave our poor spaghettified astronaut behind and zoom all the way out to meet an actual cosmic titan. Black holes scale up dramatically in our universe. They start with stellar mass black holes, which are born from collapsing stars. Then we step up to intermediate and then the supermassive black holes, the kind that sit at the center of most galaxies, including our own Milky Way. But at the very top of the food chain, in a mind-boggling category all its own, are the ultramassive black holes.
100 billion. Let that staggering number sink in for a second. That represents the estimated solar masses, meaning 100 billion times the mass of our own sun, of the black hole right at the center of the Phoenix A galaxy. To put that into perspective, this absolute unit easily dwarfs the famous TON 618 black hole, which was previously considered the heavyweight champion of the universe at a mere 66 billion solar masses.
So where is this thing? Phoenix A lives inside the Phoenix Cluster, which was discovered relatively recently back in 2010 by the South Pole Telescope. It's located a dizzying 5.7 billion light-years away from Earth, and this structure is a monster, spanning 7.3 million light-years across. Its total mass is estimated at roughly 2.5 quadrillion solar masses, and it holds the record as the most massive and highest X-ray emitting cluster we have ever observed.
And believe me, this cluster is not just sitting there quietly. The central galaxy hosts the most massive starburst region known to science. It is forming stars at a ridiculous rate of around 740 solar masses every single year. It's this chaotic, feverish environment of cosmic creation and destruction, all swirling around that 100 billion solar mass anchor.
Which brings us perfectly to Section 2, the cosmic growth limit.
With all that frantic growth and gravity that incredibly strong, a really natural question comes up. Is there a ceiling to how massive these entities can actually get? Can something that big just keep eating forever, swallowing up entire galaxy clusters without end? Well, the answer lies in the weird physics of how black holes actually feed. Surprisingly, scientists predict that black holes have a built-in thermodynamic mechanism that literally starves them once they reach a certain size. Here's how it works. As a black hole consumes matter, it violently ejects energy and gas in the form of powerful jets, or what physicists call astrophysical outflows. These jets shoot out for tens of light years and intensely heat up the surrounding gas. Because that gas is now incredibly hot, it can no longer cool down and condense. This disrupts star formation completely, and crucially, it cuts off the cold gas supply the black hole needs to keep growing. It basically cooks its own food source. Dr. Priyamvada Natarajan at Yale University totally hit the nail on the head here. Her research highlights this exact self-regulating phenomenon. The findings suggest that inefficient accretion and all this massive expelled material act as a natural, built-in cap on growth. And where is that theoretical ceiling? It sits right around 100 billion solar masses. This means Phoenix A might literally be at the absolute physical limit of how large a single object can possibly be in our universe. No way it's getting much bigger than that.
All right, let's head into our third and final section, the dark matter question. Now that we've established the upper limit of how big black holes can get, let's explore one of the most exciting theoretical mysteries surrounding them, their connection to dark matter. In cosmology, there's long been a hypothesis about primordial black holes. These aren't formed from dying stars, they're formed from dense pockets of matter in the very first fractions of a second after the Big Bang. Researchers proposed a specific category called SLABs, which stands for stupendously large black holes. What a great name, right? They define them as primordial black holes exceeding 100 billion solar masses.
Now, since these theoretical slabs are way too massive to comfortably fit inside normal galaxies, they'd just be out there, drifting in the dark voids of space. This led researchers to wonder something huge. Could these early universe slabs actually make up a significant fraction of dark matter? Could the invisible, unobservable mass that's shaping our cosmos just be a vast network of these stupendously large, ancient black holes?
It is a brilliantly elegant theory, honestly, but as is often the case in physics, recent papers have rigorously tested this hypothesis against actual observable data from the early universe, and we got a definitive answer. The theory simply clashes violently with the reality of what we see when we look at the cosmic microwave background, which is the oldest light in the universe. By analyzing the data, scientists figured out that if SLABs actually existed in those massive numbers, their immense gravity would have caused massive density fluctuations, basically giant ripples in the fabric of the early universe. But when we look at our most precise satellite maps of that ancient light, those ripples just aren't there. Multiple independent datasets confirm the early universe was just way too smooth for these giants to be hiding everywhere in the dark. As this recent study beautifully summarizes, the hard data elegantly closes the mass window. It proves that while 100 billion solar mass black holes like Phoenix A absolutely exist today, primordial black holes of that size from the dawn of time cannot be the missing dark matter we've been frantically searching for. The numbers simply do not align with the quiet, smooth glow of our early universe. And that brings us to the end of our journey for today. We've seen how extreme gravity totally breaks our perception of time, we've found the 100 billion solar mass limit of black hole growth, and we've definitively ruled them out as the universe's dark matter. All of which leaves us with a profound lingering mystery. If it isn't stupendously large black holes, what exactly is holding all our galaxies together? I'll leave you to ponder that one until our next explainer. Thanks for joining us, keep wondering, and always keep looking up.